Welcome to this explainer. Today, we're diving straight into Chapter 7 of the Pure Mathematics coursebook to figure out how to effectively reverse engineer complex mathematics. I mean, if you've ever stared at a massive algebraic fraction and just wondered how on earth to untangle it, you are in exactly the right place.
Just look at this stunning fractal pattern from the cover of Chapter 7. It completely sets the tone for the beautiful complexity of further algebra that we're about to jump into. At first glance, a fractal looks, well, overwhelmingly complicated, right? Just a chaotic swirl of colors and shapes. But when you look a bit closer, you realize it's actually built on simple, repeating rules. And honestly, that is exactly what we're going to be doing with algebra today. Taking something that looks super intimidating on the surface and breaking it down into its elegant foundational pieces.
Which instantly brings up a totally relatable question posed right at the start of the text. Why do we actually study algebra? We've all been there, staring at a page of equations thinking, why? The text addresses this beautifully, reminding us that algebra isn't just about building things up. It's really about understanding how things are put together by taking them apart.
To conquer this topic, we're going to cover 4 key areas today: the reverse process, spotting improper fractions, mastering partial fractions, and finally, solving for the unknowns. Let's get right to it.
Starting with Section 1, the reverse process. Basically, deconstructing equations.
We are completely shifting gears here from construction to deconstruction. Back in basic IGCSE or O-level math, you learned how to build equations by adding and subtracting algebraic fractions, right? You take 2 separate fractions, find a common denominator, and kind of smash them together into one big expression. But Chapter 7 introduces this reverse process, taking those complex combined equations and tearing them back down into their original simpler parts. It's literally like looking at a fully baked cake and figuring out exactly how much flour, sugar, and eggs went into it.
Moving right along to Section 2, spotting improper fractions. This is all about identifying those top-heavy equations.
Because, look, before we can start breaking things apart, we have to make sure they're in the correct format. You can't just dismantle any random fraction. You got to know what you're looking at first. So you must identify improper algebraic fractions. These are essentially top-heavy equations. In regular arithmetic, an improper fraction is something like 7 over 3, where the top number is bigger. In algebra, it just means the highest power of x in the numerator is equal to or greater than the highest power of x in the denominator. When you spot one of these, it absolutely has to be simplified using algebraic long division into a regular polynomial and a proper fraction before you can even think about moving forward.
Check this one out. See how we've got an x cubed on the top, but only an x squared on the bottom? Massive red flag right there. If you try to pull this apart without dividing it first, you will end up with total mathematical nonsense. Recognizing this one crucial step is really what separates the novice mathematicians from the advanced ones.
Okay, Section 3, mastering partial fractions. This is where we actually carry out the breakdown.
Once we know our fraction is proper, we arrive at our core tool. The text emphasizes our main goal here. We need to systematically carry out the decomposition of these rational functions. Decomposition, such a great word for it. We're taking this dense, heavy mathematical object and letting it naturally break down into its base elements. But to do that correctly, we have to recall the appropriate form. We can't just guess what the broken down parts will look like.
So, the absolutely crucial point here is memorizing these templates from key points 7.2 and 7.3. These are our blueprints for splitting up different types of denominators. If your denominator has 2 linear factors, it splits into 2 fractions with placeholders a and b. If it has 3 factors, it splits into 3 fractions with a, b, and c. These templates are totally non-negotiable. They are the architectural foundation of the reverse process. If you set up the blueprint right, the rest of the math just flows naturally.
Which brings us to Section 4, solving for the unknowns. Time to actually find a, b, and c.
Now it's time to build out those specific values. Let's look at worked example 7.1, where we're tasked with pulling apart the fraction x minus 13 over the product of 2x minus 1 and x plus 3. Our mission here is to find the hidden values of a and b that make our template perfectly equal to this expression.
And hey, no guessing required. We just follow these 3 super logical steps. First, set up the template identity. Second, multiply throughout by the bottom denominator, which, by the way, is incredibly satisfying because it instantly flattens our fraction into a straight, easy-to-read horizontal line of algebra. And third, substitute specific values for x to isolate our targets.
This substitution method is where the magic happens. By strategically setting x to specific values, like 0 or 4, as seen in worked example 7.3, whole chunks of the equation just vanish. If you have a term multiplied by x minus 4, and you decide to let x equal 4, that whole term becomes 0, and poof, it disappears. It feels almost like a magic trick. You are purposely choosing numbers that wipe out the variables you don't want, leaving only the one you're actually trying to solve for.
Using that simple, elegant trick, you can quickly solve for up to 3 unknown variables, a, b, and c, without getting trapped in endless algebraic loops. Instead of wrestling with massive simultaneous equations, you just surgically remove parts of the equation one by one until you have all your answers. It's efficient, it's clean, and honestly, it's highly rewarding once you get the hang of it.
So, once you're a pro at tearing these fractions down to their core, it leaves us with a pretty massive question. How is this foundational reverse process going to empower us to tackle the advanced binomial expansions lurking in the very next section of the textbook? Because, as we know in math, a new tool is never just for one job. By breaking these functions down, we're actually prepping them to be expanded into infinite series. But that is a beautifully complex puzzle for another time. Thank you so much for joining me for this explainer, and remember to keep looking for the simple building blocks hiding inside the complex ones.